Okay, so let's move to the next capability that we can essentially achieve. So if you look at the unique phase diagram for the LSMO, basically if you do nothing to that, if you cool it down, it's a ferromagnetic phase. Okay, but if you apply strong, I would say large or in a strong comprehensive strain, and basically once it's strained, compressively strained, it will become anti-ferromagnetic materials. So we start to ask ourselves whether we can demonstrate the first time for the same thing in any location we can control the alignment of the AFM and the AFM orders. Okay, so let me try to, I think that my time will be pretty limited, so let me try to make it a little bit fast. So we do freestanding once again, then we selectively cover the same area using, or we use the lithography to create some pattern, and we finish the growth. So whatever you ground on the freestanding layer, and basically it's unstrained. So whatever you ground on top of the substrate is strained, is highly strained. It can also be confirmed by the X-ray diffraction. Okay, so now we not only create stripe patterns, we create word-like patterns. So here we have LSMO. So of course, here is NCKU. So of course we have NCKU patterns, but the data is not really like good. So please forgive me. The next time I will try to make it updated. Okay. Anyway, so for this kind of pattern, basically we hope that in the part it is composed of anti-ferromagnetic LSMO, and the outer part it should be composed of ferromagnetic LSMO. So we can use some spatial technique, for example, nail diffraction, X-ray nail diffraction, and to reveal the strain structure. So basically, it tells us that the place where are basically orange, they are strained, the LSMO. Okay? And if you look at the outside area, and this is plot, if you look at the orange area, basically it suggests where the unstrained LSMO is. So if you are convinced by the phase diagram, if you can also convince by the X-ray diffraction, I hope that you can convince that we can essentially control the magnetization station. But this is no real evidence. So luckily we have some allies in Switzerland. So a few of my students, they went to Swiss light source. They spent a couple of weeks there and tried to use a very advanced techniques, which is called photoemission electron microscopy. And using that kind of spatial technique can spatially reveal the magnetic contrast. So okay, so in this picture, basically whatever you see, the red and blue contrast, they are magnetic. Okay, so if you look at the area that only with very light contrast, it simply tells you it's non-magnetic. But you can also try to through the analysis on the spectra, you can also tell them the configuration of the magnetization. So we hope that we can indeed convince you that the inner side is anti-ferromagnetic, and the outer, or basically the matrix, they are magnetic. Okay, so let me try to guide you through to how we can essentially do using this kind of combination. So here I would like to guide you back to the original stripe architecture. Okay, so we hope to do a nice comparison. So to do so, we hope that we do everything in the same sample. Okay, so we have a few areas. So later we will have an area, we do the transport along this part, which is composed of ferromagnetic unstrained LSMO. We also do the magnetic transport on this part. This is a highly strained anti-ferromagnetic LSMO. We also want to do a transport along this direction, which is multi-junction composed of AFM and ferromagnetic orders. Okay, so let's take a look what we can have. So this is a typical magnetic transport. So if you do the magnetic transport as a function, you measure the resistivity versus the temperature as a function of magnetic field. Okay, so this is basically something you have. So you will see that when you apply larger magnetic field, the resistivity goes down. So this is the typical LSMO we have. Okay. All right, so if you look at on the left side, so basically we do the magnetic transport on the anti-ferromagnetic LSMO. So originally it's insulating. So this is a classic feature for the anti-ferromagnetic species. But once you apply large enough magnetic field, you can suppress the interactions in the materials. And so basically you can suppress or you can induce the phase transition once again. So to that, compared to original CMR value, which is around 50%, here we can have like 1,600%. Okay, so let's take a look at what essentially happened if you do something across the boundary. So this is, we do the same thing and we get the magnetoresistance value. Now, the CMR value can reach as high as 2,600%. So that means that by compose this kind of feature, we might take advantage for the interaction between the adjacent ferromagnetic layers. So let's take a look. So if you have been to the second floor in the Department of Physics, in QFort, basically we have a very, very nice low temperature scanning probe microscopy, which can be, we can go to low temperature, but we can also apply high magnetic field. So this is something that we have. So if you look at the typical picture, that you do it at 10K, all right? So if you look at, you simply enlarge the pattern L and S. And in the inner area, basically there's no response for the magnetization. So this is the antiferromagnetic region. So if you look at the outside area, it's composed of ferromagnetic matrix. They are basically unstrained LSMO. So if you try to enlarge the magnetic field, you apply, for example, you start from 1 Tesla, 3 Tesla, 6 Tesla to 9 Tesla. So this is something you can have. So what we essentially see is that the dark or the bright contrast start to become blue. So it also suggests you that through the application for the magnetic field, basically you will assist the anti-ferromagnetic spaces to become ferromagnetic one. So thank you. So I think that it's also it's just a start. And simply we are essentially looking at how close the ferromagnetic species can be, and once we get it close, whether we can enhance the interaction further. So so far we don't have the clue yet. My students are working very hard for this. All right. So I think let me try to give you a summary schematic. So that means I hope that through this talk I can convince you that we are indeed to pay a lot of attention to the creation of to the modulation of the quantum materials. Basically, we focus a lot on complex oxide. So this is the twisted architecture that we developed, and in the end, we still have a lot of play to play, so-called the cell proximity effect in the same material system. Okay, so by the end of my talk, I would like to acknowledge, I would like to thank all the founding agents and NCKU and QFort, of course, and also I would like to thank all my collaborators or colleagues, and it is actually their great help which make all I had to talk about possible. And in the last slide, I would like to thank all my group members. They guys actually work very hard, and so that I have the chance to have some data to present on this stage. All right, so once again, thank you for listening to my talk. Thank you.
Thank you, Zhanqi. Very exciting presentation. Any questions? Okay, actually, I got a question. Because when you are using your oxide layers, you have two surfaces.
Yep.
And on the surface, you probably have a dangling bond or dimers.
Yes.
And what's their role and what's their impact on your study result?
And actually, I would say fortunately, the dangling bond didn't do too much effect during the growth. For example, as I mentioned before, for the complex oxide system, they are bonded through ionic bonding. So that means the dangling bond compared with the ionic bonding energy, the scale is a little bit different. So basically, when you finish the growth, they will only see through only look at the template you provide at the bottom. So if they intended to form ionic bonding, basically the dangling bond wouldn't do any effect to the final structure.
So when you prepare your devices, you don't need to anneal or any
no, we don't.
cure.
Yeah, this is the advantage. We don't need to do any anneal. But the process, the only disadvantage I would say is that during the original growth, it should be done at high temperature. Okay. Yeah, this is for the thermodynamic issue in complex oxide.
Okay, thank you. Yeah, please.
Thank you for the very nice sharing and update of this technology. I have a question about the geometric effect. So 2 questions. So for when you try to fabricate this freestanding layer, how big size you can achieve to maintain still the very stable mechanical property?